Hi everyone, my name is Marco Abela. I am a product manager in Google Cloud Storage, which is our object offering, and I specifically focus on storage for AI/ML. So we're going to kick this off with kind of like a brief introduction and overview of our different storage solutions, what we've been working very hard on over the past year. Then I'm going to get into our Cloud Storage Fuse offering. I will talk about Anywhere Cache, which we just GA'd and announced the GA at Next. And then Dan, my colleague, is going to be coming up after and talking about our new managed Lustre solution. So to kick it off, we know that for AI/ML, a lot of folks, the main focus is typically compute, GPUs, TPUs, which is awesome. But you got to keep those GPUs and TPUs well fed. And so storage is a critical key piece of the AI pipeline. And choosing an improper storage solution can really negatively affect your GPU utilization. If storage is a bottleneck, your GPUs and TPUs are just waiting there, sitting idle, waiting for data to come in before they can begin to process them. And this is throughout the entire pipeline, from your initial data preparation, which is where you're taking your raw data, cleaning it, and then passing it down to training, where you are going ahead and iterating on those samples. Then you're generating a model, you're loading that model from inference, and then depending on what your inference is, let's say it's Gen AI content media, pictures, video, you're then serving those that content back out. And so throughout that entire pipeline, storage is absolutely critical. And the two kind of like the industry optimized storage that's really used for AI/ML is there's object storage, and then there's parallel file system. So on the object storage on the Google side, we have our cloud storage, which provides persistent read and write storage with virtually unlimited capacity and providing very, very high aggregate throughput. Our parallel file system, our new managed Lustre offering that Dan is going to be covering more, provides persistent storage, capacity in the terabytes to petabytes, but really it focuses on ultra low latency to really drive down a specific workload profile. And so what are the typical storage requirements that we see for AI/ML, which are can be similar to other workloads, but also different from other workloads? But in general, what they really mean is lots and lots of capacity. So from your total storage corpus to then the actual amount of data that you are either training on or the models that you are loading, you can need anywhere from terabytes to exabytes of data. From a performance standpoint, from bandwidth perspective, very, very high aggregate throughput. So we're talking about terabytes per second of throughput for both reads and for writes for checkpointing. And then also millions of requests per second. So what we refer to as QPS in the traditional storage world, also known as IOPS, needing millions and millions of these requests while serving that high bandwidth. Low latency for reads. And then last, also something that affects all of this is also the nature of this workload, whether it is, constant or spiky and bursty, depending on the different stages in the pipeline. Stuff like checkpoint restores are bursty, model loads are very bursty, but basically just depending on the different pipeline, they can have all of these different storage requirements, a subset of them, but these are typically what we see in the AI/ML pipeline. And to give a very focused example of that, checkpointing and serving, I can give you a pretty consistent, very predictable definition of what the storage requirements for those are. Kind of the most difficult one to have a consistent definition on, and I've been working with hundreds of customers over the past few years on getting their storage right for their AI/ML pipeline, is really training, where there is the most variance in terms of I/O patterns. So to give an example here, right? The top example here is you are basically just reading something sequentially, whether it is each file or object is an individual example, or you have a structured file format like Parquet or TF record that has many samples in it, and you're just reading that end to end. You can have very nice throughput, very nice performance from object storage and just reading that sequentially. Then you can also have, again, using these now structured file formats that have multiple samples within the same file, like Parquet or TF records. You can also have where each node gets a file. There are, let's say, 110 gigabyte size files. And within that, each node begins randomly sampling within each object or file. And then at the end of an epoch, those all get shuffled back out and sent to different nodes. Then you have fully random, which is at a certain training step, they are reading across files to get a sample and then load it into each node. And then you have multimodal, which you are doing a little bit of everything. You are doing metadata lookups, full object reads, random lookups in databases. Stuff can get really, really complicated with multimodal, where you need both ultra low latency and very high throughput. But basically, this just shows you what I talked about before, the different performance aspects. It shows you in training how different different training profiles can kind of have all of those at the same time. Some of them, a subset of them. So what we're going to be talking through the rest of this presentation, over this past year, we have been we've been working extremely hard on basically solidifying our storage for AI ML portfolio. Many new announcements that we had at Next this year. The key things that we're going to be talking about throughout the rest of this next hour is Cloud Storage Fuse and the new enhancements there, Anywhere Cache, Rapid Storage. Manjul already covered Storage Intelligence, and then Dan is going to be covering Managed Lustre. So let's start with Cloud Storage Fuse. So Cloud Storage Fuse, for those of you that are not familiar with it, very simply put, it is a way to mount a bucket as a local file system. And you can interact with your buckets as files using very basic file system semantics. We invested very heavily on this over the past, I want to say about 3 years. And boy, is it a bet that really paid off. The reason why we see what we were seeing before was customers had this data in object storage, and then they would just copy it down locally for two reasons. One was just semantics. Their application just knew how to talk to a file system, and they didn't want to rewrite to use object storage, or they simply couldn't even do that. Or for performance, bringing it in locally, get from the performance of local SSD. But the problem with that, what we were hearing from customers, is having to deal with that, managing the data transfer in and out was just a complete nightmare, especially as the storage profile was growing. And so that's where we built Cloud Storage Fuse. And most importantly, we also, one of the very, the main value adds also of Cloud Storage Fuse is that while originally we were intending it as for following these different use cases of, again, you want the portability, now it is kind of our high performance client of choice because of specific performance optimizations that we built natively into the client, including our file cache, our parallel download feature, and streaming rights and hierarchical namespace bucket integration, which I'll cover slightly more in Dale. But what I mentioned before is, boy, is this a bet that really paid out. And one great indicator of this is we also have a managed CSI driver. So for the GKE, the Kubernetes, the people that are familiar with Kubernetes and want to use familiar Kubernetes API, we have a CSI driver that basically deploys GCSFuse as a sidecar that you don't have to really manage or do anything about. It's just this managed offering. And we have just seen explosive growth on this with some of the largest AI ML customers in the world using this solution. So I think last year at AI Infra Day, we had just announced the Cloud Storage Fuse file cache. So I'm not going to spend that much more time here. But the way I'm breaking this down is what are we doing for training? What are we doing for serving? What are we doing for checkpointing? So for training, the cloud storage, the file cache for cloud storage Fuse is what it really helps. And Toyota was a great example of this. They presented with us on stage last year. What they saw was a 33% faster second epoch time, 20% faster total training time. And as you can see clearly from this chart, they also saw they got a cost reduction from those cache hits than just being served locally and not going back to GCS. Our GPU machine types come with I think it's up to 6 terabytes of local SSD currently, maybe even higher, 12 terabytes now. And so that is a perfect use case for this file cache, where you simply just point it to a local directory, which is backed by local SSD. You can begin to use that. You can use hyperdisk volume, or you can even use, some of our customers actually even use an in-memory file system such as TempFS to really, really get the screaming fast performance. From an inference perspective, what we worked on over the past year is the main thing that we've done is this parallel download feature, where the results have just been absolutely phenomenal. So if you take a look at just like general model loading out of the box that comes with some of the generic frameworks, the main ones that are used is FSspec, and there's a flavor specific of GCS, of cloud storage for FSspec called GCSFuse. And one of the main like takeaways from this also is like, just don't use that. It's a very poorly written data loader and model loader. And so in working with customers, they tell us like, hey, these models are getting bigger and bigger, and we need to be able to pull them as quickly as possible, both from the inference perspective or from the checkpoint restore perspective. And so what we did is we built this a parallel downloads feature, which actually uses the file cache, some of our file cache functionality, where we use the file cache as a staging buffer. And we basically spin up multiple workers or multiple Go routines that go and fetch this file as quickly as possible. And as you can see from this chart, the performance improvement is just phenomenal, right? 9x faster model load with parallel download. Someone was asking about VLLM before. This is done with VLLM, and you just see, again, all the way on the left, FSspec. If you just use Cloud Storage Fuse on its own, it's still going to be better than FSspec. But you use Cloud Storage Fuse now with parallel download, and you're going to get 9x faster model. The next, and then the last one here is checkpointing. So for checkpointing, one of the things that we did is we kind of we built hierarchical namespace bucket in cloud storage. And when you use this with Cloud Storage Fuse, it's kind of like a match made in heaven. So what is HNS? HNS is hierarchical namespace buckets. By definition, in object storage and cloud storage, it is a flat namespace. And so traditionally what we do, or what customers do, is we emulate folders or directories by just slashes in the file path, so prefixes. With HNS, with hierarchical namespace buckets, we now have a more true a folder format, a hierarchical namespace. And what we get as part of that is, one is atomic folder renames, which is critical for checkpoints. The way that the checkpoint libraries are written, when they detect a file system, they just assume that you can do a directory rename and it is atomic. But in object storage, again, that doesn't exist. It's an individual object name rename every single one. So in a checkpoint, that means we're now going ahead and renaming every single file. Now with hierarchical namespace, that is atomic. And so that becomes 30x faster. And it also provides up to 8x initial higher QPS. So again, you have HNS, which gives something more hierarchy. You have Cloud Storage Fuse, which mounts a bucket as a local file system. Get the two together, and you really have a very perfect and ideal solution. And then the second thing that we did is that we also improved our write mechanism. The way that we started with Cloud Storage Fuse is first we wanted to get the read path fixed, especially like in AI/ML. It is mostly a read-heavy workload. The only kind of outlier there is checkpoint writes. And so the way that Cloud Storage Fuse used to work before was that writes was that we staged them locally first, and then only when you closed them or you did an fsync, would it then get uploaded to cloud storage? But the problem with that, or many customer complaints was, well, then I need to provision enough space locally in order to stage everything, which, depending on my parallelism, can just grow out of control. So now all we do is we have a memory buffer, and we start uploading directly. So not only is it more efficient, but it's also much, much faster, where we're seeing 40% faster checkpoint, a reduction in 40% of a checkpoint write time. So very, very efficient, and lots of work that we put in cloud storage to really make it, to really make it stable at high scale use cases. Very quickly touching also on checkpointing and the different options that we have. This is kind of a very simplified view of also what we recommend from a checkpoint perspective. So on the left-hand side, we have cloud storage, which again is cloud storage fuse with HNS and streaming rights. And here we say, 5 to 10 minute frequency checkpoint, support up to 1K nodes. Now we have customers that exceed that. We have customers that have lower than 5 minutes, but general rule of thumb, this is kind of how to think of them. In the middle category, we have parallel file system, which will improve that further. So with managed Lustre, we typically say we can support up to 1 to 5 minute frequency checkpoints at 1K nodes. And then what we just announced at Next is our new multi-tier checkpoint solution. And this is really intended for customers checkpointing at the largest scale. 30-second frequency checkpoints at more than 1,000 node scale. We did this with Llama 70B at more than 1,000 nodes, and we were way past the 30-second frequency checkpointing. The way that this works is that we use an in-memory RAM disk, and we do checkpoints in memory and a local node and a peer node. And what this allows, and then based on a higher frequency, those then also get backed up to cloud storage, actually using GCSFuse, which is wrapped under this solution. So the benefit of this is that you can get in-memory performance. So you can do very, very high frequent checkpoints without burning stuff like local SSDs. You get very high throughput because you're using the intra-cluster network. And so what that also means is, from a checkpoint restore perspective, you can either restore from a local node, from a peer node on that same super fast east-west network, or in the worst case scenario, if you have a total catastrophic failure, or you just want a go back to an old point in time for a specific test, you can then restore that back to GCS. So these are kind of the 3 different solutions and where these line up from what we provide from a general recommendation. Yeah.
So question on Kimberly-Bates return group. The multi-tier checkpointing, is that just for cloud storage?
So it is for the backup part of it is for cloud storage, but it's a GCP based solution. So it's on GKE, and so it's a GCP specific solution.
Okay, but it's not doing the Lustre.
Correct.
Okay, so it is it's just addressing the object storage, cloud storage object for that.
Yeah, and using memory in each node, not GPU memory, to create a RAM disk. Yeah.
So where the data resides is object. I use this for the object storage, even though I may be using RAM. Okay, got it. Okay.
And Jim Sprinsky, Zero Defect Computing. Just to follow up on that, just so I'm clear, right? These are files that would be input to initial model testing, or is this just loading the model itself or pieces of the model, or is it everything?
Yeah, so these are during your checkpoint workflow where you are actually saving the state of your model weights. This is what that is, right? So it's actually, this is both primarily a write workload, and then when you need to do a restore, in the case you have to do a restore, right? The larger the number of nodes and GPUs you have in a cluster, the more likely you're going to have a hardware failure. And so that's where you're then going to do a restore. And so rather than having to restore back from cloud storage, you can restore from an in-memory disk in a peer node on the same network.
So which shortens recovery time, which gets you back to running as quickly as possible.
Exactly.
A failed Kubernetes node, for example.
Exactly.
Got it. Perfect. Yep. Thanks. Just want to clarify.
And so just to wrap up this part on Cloud Storage Fuse, this is a customer example. This is Assembly AI, which is an enterprise grade speech AI company that processes petabytes of audio. And so I worked with Ahmed this past year, that he was having challenges, and they have lots of small file challenges, high latency, and because lots of small files, there's also lots of operation costs. And so we took a look at his workload. We saw there was lots of metadata lookups. And so what we said was, hey, why don't you try CloudStorageFuse with HNS? With HNS, we also do a huge reduction in metadata lookups because we clearly know if something is a file or a folder. And regularly in object storage, we don't know that. We have to go and figure that out. And so what he did from this test in this, to really show you the power of this, he saw a 10x increase in throughput and a 15x training performance improvement. So really, really cool to see an actual example of, again, using this solution end to end. All right, so now we're going to talk about Anywhere Cache, which, as I mentioned before, this is something that we announced at GA at Cloud Storage Next this year. So who here remembers the turbo button, that little red button on your computer? You would press it. You don't know what it did, but your computer would all of a sudden start making lots of noise and stuff would start going faster. So this is actually, I don't take credit for this. Someone from our engineering team came up with this. He probably should work in marketing. But Cloud Storage just got one, right? So it's a very simple and efficient way. You just enable it. I'll show you how simple it is. And what this does is it improves performance by co-locating storage in the same zone as compute. So cloud storage is a regional offering. Now it becomes Anywhere Cache makes it now a zonal offering that's as close as possible to your compute. And not only that, but it's also on SSD. So you have zonal co-location, you have SSD, stuff is going to be faster. And as part of that, again, one of the main value adds of this is just how simple it is and how easy it is to use and that you can use it anywhere. So no need to refactor code, no need to change what path you're reading from. It's literally you enable it and you just continue reading from your bucket as you did today. It just works. So you press the turbo button, you enable Anywhere Cache. What happens? It is there is a significant time to first byte latency reduction. On the top here, you can see a 70% reduction for regional buckets. And then for multi-regional buckets, which I'll talk about also, very special, unique value that we have when combining Anywhere Cache with multi-regional buckets, is a 96% reduction in latency. And what I have here also on the bottom right is this is a large Gen AI customer that uses Anywhere Cache for model load with multi-regional buckets. Very, very awesome use case. So this is a customer that grew out of a single region. So they were able to get many, many GPUs in one region, and then they got many, many other GPUs in another region. And traditionally, the way that they had set it up was one region for training, one region for inference. But because inference was so critical as their user demand was picking up, they also wanted to be able to use some of the capacity in the training side also for inference. And so what they had to do before was, one was they had to do all this manual data movement around every time, keeping everything in sync. And the second thing also that they were seeing, and in addition to that, that also had cross-region egress costs associated with it. And then the second thing also is that, again, when you're deploying at scale, 1,000 node scale or higher, tail latencies are going to make a huge impact. So you're not going to notice it if you're deploying, 10 nodes or whatever. But they were seeing that tail latency model load on, one node or 10 nodes of that 1,000 node cluster was just keeping everything like bottlenecked. And so what they did is they moved to a multi-regional bucket, cloud storage multi-regional bucket, where they stored the data once. They spun up an Anywhere Cache in each of the two zones that they have in different regions. And then they just began reading from it. And what they saw from this is a model load is a highly cacheable workload, which you can see here, 99% cache hit. And it completely eliminated their tail-end latencies. And it also helped them save money in network egress costs.
Just a question is independent. Are you using some sort of predictive cache calculation to do this, or is this all just?
No, good. It's a good question. So we have two different cache ingest behaviors. You have a cache on first read, or we have a cache on second read. So yeah, if you want to make sure that you're ingesting on that your data is highly cacheable, you can enable the second one. So read it twice and then ingest. But the first one is basically if you get a cache miss, we'll load it into the cache, and then once it's ready, once it's in there, if you do a repeat read, you'll get a cache hit.
Okay, but you don't do any predictive population.
No, we do not.
Okay. You were talking about the increased or decreased latency to first read, and I was wondering if you were doing.
Yeah, no, that's based on a cache hit versus a cache miss.
Okay.
Yeah. So under the hood, again, what's happening here? So it's fast, it's SSD backed. Not only do you get lower, up to 70% lower read latency, it also supports 2.5 terabytes a second of additional throughput in addition to what you get from cloud storage today. Very, very simple. Again, completely transparent to your application. Just click a button, enable it, and you pay for what you use. So it's very, very efficient. Pay for what you use, and it auto scales to the capacity that you need. So kind of like what customers would expect from a cloud storage offering in a hyperscaler cloud.
Is it also considered ephemeral? Will it go away when you're not using it?
So it doesn't go away when you're not using it. You can pause the cache if you want. That's another management capability we have, that you can just pause it, or you can just disable it and it goes away.
Okay.
So
I mean, if you're using this for an ephemeral workload, it would go away with that workload?
Yeah, if you enable it on a bucket level, when you're done using it, you just disable it.
Okay.
Yeah, question, Bart Jongens from Bitcoin. So it has a certain price because you're adding SSDs and so on. You say it's pay per use, so if I say I'll enable 100 gig, but I'm using only 50, then I'm paying for 50?
No, you don't specify a size, actually. You enable it, you begin reading, and then based on your cache ingestion policy, whether it's that on first read or second read, that just gets loaded in there, and you're billed for the bytes that get ingested in there. So you don't specify a size.
But if I have a terabyte database that I start reading, I can have a cache of 1 terabyte then.
Yeah, so it's a chunk-based cache. So we ingest in 2 megabyte chunks, and so the way that works is specifically for the analytical workloads, you have a very high portion of hot data within a larger file, and so what that benefits. In AI ML, you're typically loading you have a data set for training, you're reading that entire thing
Of course.
But for these analytical workloads where you have a giant set of Parquet files, and you have very specific, row or table that you're reading, it will only ingest that in 2 megabyte chunks.
Mm-hmm.
Do you have any customers running any cache with confidential computing?
I'm not sure.
Okay.
What is there a specific reason you asked that? Why confidential?
Yeah, I mean, it seems like it should be decoupled and not a problem, but I'd just be with sort of the caches and the way you'd set up confidential computing,
Yeah, it should. Like I said,
just wondering if you had any customers that it seems like they'd be more complex than just turning both on and magic.
As long as you have a connection to a cloud storage bucket, it'll just work.
Okay.
So another very interesting thing that we do to make it very easy for customers to use or understand if they're a fit is we also have a built-in recommender. So if you log into our our web UI, you look at a bucket, you'll actually see you'll see a thing that says recommender, and it will tell users how cacheable a workload is, so what their cache hit percentage is. It will recommend the optimal cache configuration, and it'll tell you also your throughput and your cost, including cost savings. So to your question before, also around how do I help understand like the cost and everything, this recommender will actually give you a very precise information on whether your workload can benefit from this or not.
Jay with Nexus Tech. previously we saw a recorded demo. It also had the Google recommends UI UX label at the very top,
Okay.
in the web UI. Is that a consistent web UI that you're saying like these are the Google recommends and that should stand out on the page for the user?
So this is specific in our cloud storage bucket page. So it's within that and specific to the Anywhere cache. How it flows back up to the larger recommendation, I'm not exactly sure. But I can look it up after. Maybe we can talk.
Thanks.
All right. So the other thing that I mentioned before is a multi-region bucket in cloud storage is a very differentiated offering, right? So we have our single region buckets, which are optimized for performance. We have our dual region buckets, which gives you performance with higher availability, right? And then we have multi-region, which has higher availability but lower performance because you don't know where the data is. And so now what we have is we have the ability to attach a multi-region bucket to an Anywhere cache and basically not have to have any trade-offs. So you'll have the super high performance. You'll have storage that is co-located with compute in the same zone and backed by a multi-region for the higher levels of availability. And what's really awesome about this too is that with this, when you're doing a read from a multi-region bucket, you're also there. Traditionally, there is a multi-region egress fee that you are paying. With this, that gets eliminated. So we make it much more consumable and much more attractive offering to use Anywhere cache with multi-regional buckets, and again, get the benefits of the best possible performance and the highest levels of availability. Again, without having to worry about this data movement overhead.
So in the recommender that you have, does it give you, and you go through this process, does it give you the expected throughput with this multi-region Anywhere cache hit rate?
Yes. Yep.
Combinations?
Yeah, exactly. It'll show you the peak throughput that you'll be able to get from your cache data, and more specifically to what you just asked, we also show a very specific savings in terms of multi-regional egress that you will get from Anywhere cache.
That's really cool. Thank you.
Yeah. This is the last thing. I just wanted to show you guys a very quick demo. So here, this shows you how easy it is to use and the performance you get out of it. So under configuration in your bucket, you have a Anywhere cache. Here it's already running, but it basically shows you the zones within the region. You choose the zone, and then you simply check it off, and you press enable, and that's it. The Anywhere cache goes ahead and starts building. And then what we have here is we have a demo that does a comparison of this is a model load simulation. So this is a 10 gigabyte file. On one side, we have using just the GCS standard bucket in order to read this 10 gigabyte model. And on the right here, we have Anywhere cache. We have a bucket that has Anywhere cache enabled. And so what you see from this is when we kick it off, is you'll see that with Anywhere cache, it takes about 47 seconds to complete. So these kick off at the exact same time. And then with a standard GCS regional bucket, it takes about double that. So we'll jump to the end here, but it's about 93 seconds. And then as part of this also, we have inside of our observability metrics, we have, you can go ahead and see performance monitoring your cache hit rate, monitor the throughput that you're getting from it. So just treat it like its own management object that you have insights into what you're driving and what performance you're getting out of it.
Just a quick question for this demo. I assume that you pre-populated the cache already?
Yes. Yep.
Okay.
Yeah, this is cache hit. So, and model load, again, like we showed before in that that example before of that Gen AI company, it's a highly cacheable workload. So.
Okay. Yeah.